Okay, so good morning. So yesterday we were looking at these asymptotic symmetries in Chern-Simons theories with application to three-dimensional gravity. So let me recall the main ingredients that we used and we will continue to use today. So the first is clearly what is the Chern-Simons action, but I stress that what is interesting for us is the fact that I can rewrite it as an action which is already in Hamiltonian form. So once again, when I start, I just recall some formulas that you already have in your notes. Plus a boundary term a priori. And given the form of a kinetic term here, I can easily extract the form of a Poisson bracket between the canonical variables. So essentially, I know how to compute the Poisson bracket. And then it's something that I will do extensively in the following. Just to recall it, from where is this formula is coming from? Just the fact that here there is a trace. And the fact that here I have a trace means that the term a theta a rho dot minus a rho a theta dot is actually something that I can write in the form gamma ab a theta a sorry, theta rho b plus blah, 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 where this gamma ab is just the killing metric. And once again, I keep everything general, but you can think of this generator being the SL2 generators, and that you can use the JA that I introduced yesterday. So the form of a kinetic term dictates what is the form of a symplectic form here that I can throw inside and I can use to define the Poisson bracket. So typically, maybe you don't tend to see this one because you are used to have something which is of a form PQ dot, and simply this matrix in this case is a diagonal matrix, well skewed. So all entries are one in the right place in such a way that when you contract QA with PA with DQ with Q dot A, you get the usual kinetic term. Okay, so that was the first important information. And the second important information, so Chern-Simons form, from where you can derive the action. And the other important information is that the generator of gauge transformation takes the following form. So these are formulas that I will try to keep on the blackboard for a while. So let me take the time to write them. And the way to define, so what are the important properties of this object is that, in general, the gauge variation of any function along the phase space can be written as the Poisson bracket of this object with f. And the other thing is that how can I determine Q? Well, Q is determined by this condition, so what I know is actually its variation. And as I stressed, if lambda is just an arbitrary parameter, I have no problem in integrating this variation. So this variation is just the delta of lambda a theta, without any problem. But if I impose some boundary conditions, I may discover that the gauge parameters that preserve the boundary conditions have a non-trivial dependence at the boundary on the fields. So it could be that in order to have something that preserves a boundary condition, and may have some lambda that depends on AT. In that particular case, it's not guaranteed at all that this quantity is integrable. And this is one of the cases that we will see also in more complicated setup. But the key ingredient is really this one here. Okay, I think that's what I needed. Okay, so that is really very general. It applies to any Chern-Simons theory, any set of boundary conditions. Now it's I'm working with a sort of with a particular setup. Which means that I'm gonna making some choices of boundary conditions and gauge fixing. So I want to work with a theta which is free at the boundary. Which means that delta a theta on the boundary is free. A consequence of this choice is that delta AT at the boundary must be equal to 0. We discussed this, otherwise my action principle is not well defined, because I have to fix, so this is sort of Dirichlet boundary conditions. I have to fix half of the variables that I have at the boundary. So these are somehow my boundary conditions. On top of the boundary conditions, I added the gauge fixing condition. A priori, I'm not forced to do it. I could even work with an arbitrary gauge. I will have additional gauge symmetries, and then my asymptotic symmetries will be the quotient of all symmetries divided by the quotiented out by the proper gauge transformation. Instead of working with this quotient here, and in many cases in the literature, what you do, so you pick up a smart choice of gauge fixing such that all the residual gauge transformation becomes global symmetries. That is not something that it's clear a priori. It's not clear a priori that what I have chosen was correct, but we checked a posteriori that indeed it was. Okay, so it was the correct gauge fixing. So well, let's write it. It was a rho. And this is a gauge fixing condition. Okay. And now I define my setup. So we can be lucky or unlucky. So I fixed the problem. Now I can only compute what are the residual symmetries and possibly the associated charges, and see what's going on. So it could be that I made a mistake, I didn't do a good choice, and the characteristics that I obtain are either infinite, and this means that these boundary conditions are not good then, or 0, and this means that, well, there are no global symmetries left with my particular choice. And it depends on the choice of boundary conditions that you make, so that is very important. So this is a setup in which somehow changing boundary conditions is pretty easy. You just play with these Lie algebra valued fields, and you possibly see what's going on. Now, I will show you that with this choice, I made a good one, and so I'm gonna find some residual symmetries, and then we will see how to modify this setup in order to really describe gravity, because that remains just a sort of working example to understand better. Yes?
So I see that guys could be unlucky in the sense that maybe you have no orthotic symmetries, but in order for them to be infinite.
No, okay, so Yes, in this particular case, we are in a kind of very good situation. Well, it could have been infinite with a different choice for a row.
Very depends on the
Well, once you choose the function b, everything, as you will see in this particular case, the radial dependence just goes away. So that is another way why this choice is convenient, but a priori that is just a consequence of this choice here. I mean, Dario was anticipating that one problem that I can have when I compute charges. I told you that I want to compute the charges at infinity. There is a row dependence. I have to take the limit for rho goes to infinity, and they could diverge in this limit. In this particular choice, that I motivated it just by the sake of fixing completely the proper gauge symmetry. In this case, there is no. You will see there is no radial dependence anymore in the charges. So in this particular case, you don't have any problem, but it's just a result of my choice here. So you can even cook up gauges even in the Chern-Simons formulation. In the metric formulation of 3D gravity is even more manifest that you may have something that diverges, but you can do even in Chern-Simons, just up to you. The fact is that people typically in Chern-Simons do this. And so it's rare to find a paper that is not fixing a row, either to something or like this or to zero. But in both cases, you just factor out the radial dependence because it's convenient, but it's not mandatory in a sense. And okay, so that's set the setup, and now let's look at the residual symmetries. And I'm calling them residual symmetries here because I haven't proven yet to you that they are asymptotic symmetries. So what I'm just doing is just look at what are the residual symmetries of my particular gauge symmetry. Okay, with the argument that we discussed yesterday, I could anticipate that they are asymptotic symmetries in the sense that I've shown you that there is no anymore proper gauge symmetry into the system because there is no anymore an arbitrary time dependence. But let's say that for the moment I'm just solving a simple problem that is classify what are the residual symmetries of the system. And be careful that this kind of strategy here is applied to this very specific system, but it's the strategy that you apply to any system that you want to analyze asymptotically, essentially. We will do the same in gravity in 4D in asymptotically flat spacetime. So you set boundary conditions, and then you look for residual symmetries, then you compute the charges. Charge is different from zero, it is an asymptotic symmetry slash global symmetry slash maybe in an improper way, say large gauge transformation. You compute the charge is equal to zero, too bad, or well, maybe too good. So you just discover the residual gauge transformation. Okay, and if you are smart enough or lucky enough, you fix a gauge fixing such that all residual gauge transformation goes away, but it's not always possible even. So sometimes you can find people say that so fixing boundary condition and finding asymptotic symmetry is not science, it's an art, in the sense that you have a choice. So you have to choose what are the boundary conditions, and then you see what are the consequences. But the boundary conditions are crucial because it really defines for you the theory. So a theory is not defined, giving an action is not enough. You have to give me an action and a set of boundary conditions. I change the boundary conditions, I change the theory. And well, you can look at from this perspective, and it's just okay. Yes, you change the charges, whatever. No, so if you want to have something more quantum, somehow I change the boundary conditions. I change the boundary theory, for instance, in an holographic correspondence. Okay, so it's really a very crucial. It's really a crucial ingredient, and. Okay, so as we recalled yesterday during the discussion session, so the key is just looking at the gauge variation of a gauge fixing condition. That is also the same order that you typically use in other cases. So you impose the gauge fixing. First of all, you look at what are the conditions imposed by the gauge fixing, and then you see what happens for the additional boundary conditions that you imposed. So this is true everywhere in the bulk, including the boundary. This one is something with a condition that I fixed just at the boundary. So that is really a boundary condition. So, but let's start from the first condition is to see what are the residual symmetries that preserve the gauge fixing. and the residual symmetries that preserve the gauge fixing. If I want to preserve the gauge fixing, I have to impose that this variation is equal to 0. But having this variation equal to 0 means that lambda must take this particular form. And well, just another comment. Yesterday I told you that there is no dependence on time. Say why the hell when you write a t here? Well, it's simply because I haven't said that it's constant in time. I said that the time dependence is fixed. So the dependence on t is a specific dependence in time. So, for instance, typically there are a set of boundary conditions in which all these, functions become chiral. Having a chiral function means that for any value of theta, the value of t is fixed, because that becomes just a function of x plus or x minus, depending if it is chiral or anti-chiral. But so it's a fixed dependence on t. Okay. Okay, and well, the other small information was that that is not part. Yeah, sorry, I should have done the opposite, because that was kind of a consequence of stuff, and then I will copy back the other one. So these two choices that I have made also tell me that on the constrained surface, this a theta take this particular form. And similarly, the same is true also for the Lagrange multiplier, for different reasons, but the final result is exactly the same. And both reasons, even if they have a different interpretation, they boil down to the fact of imposing the equations of motion. Okay, and then I just copy what I have written before, but delta rho equal to 0 implies that the residual lambda takes this particular form. Lambda t theta b rho. Okay, and now we can go here, and now we can see, here I was saying now I have to see what are the additional conditions imposed by the gauge, by the boundary condition. And here I've chosen to begin with a very simple case in which the boundary conditions are not imposing any additional constraint, essentially. Why? Because if I look at dA theta, delta A theta, starting from that, essentially delta A theta is induced by a delta A theta, which is equal simply to delta theta lambda plus lambda, A theta lambda. But since A theta is free, A theta at the boundary is free, means that A theta is free. And as a result, I have no constraints on lambda. Okay, this is not the case in general. So we will see shortly another case in which instead I have some constraints on the asymptotic form of A theta, and these constraints on the asymptotic form of A theta will definitely induce some constraints on the asymptotic form of on lambda, which means on the asymptotic form of the gauge parameter, okay? So this is just the result of the gauge fixing. Then I have to check what happens for the gauge, for the boundary condition. For this moment, I have chosen boundary condition that do not add anything, so no complications, because in this way we compute immediately the charges, which is the next task that I want to do. And okay, so no additional conditions from here. And now we can look at the charges. Okay, so we completely characterize the residual symmetries. Now let's see if they have an associated non-trivial charge, yes or no. And we go there, and well, we have a nice formula here. We know that with this boundary condition, lambda is completely free. This means that I can trivially integrate this variation. If I can trivially integrate this variation, what I find is that q lambda is just minus k over 2 pi, the integral over d theta, trace of what? I just substitute the value that I have there, but then I have a b minus 1 lambda b times a b minus 1 a theta b. And then you see these two guys goes away, and the other two goes away as well, thanks to the cyclicity of the trace. So in practice, eventually, my boundary charge just take this form. So it's lambda a theta. And here you see what we anticipated well a while ago, is that all the radial dependence in all the variables that I'm using, both the gauge parameters and the canonical variables, is encoded into the functions b. And just to fix the ideas, example, for instance, b could be e rho L0, where L0 is one generator of SL2. Okay, so all radial dependence is inside this B, but the B goes away from the charges. So in this particular case, I don't have to struggle about possible divergences. So it's another useful bonus of this example, that one typical complication that I can encounter is simply not there. And another thing that we can do is to look, so first observation, for any small lambda, which means for any residual gauge symmetry, I have an associated non-trivial charge. So all of them are asymptotic symmetries because they have non-trivial associated charges. So then we discover something somehow new. It means that in my symmetries, I have a parameter which is an arbitrary function. Because it is an arbitrary function at the boundary. Sorry, maybe here is easier. So this object here is an arbitrary function, well, to be more precise, is an arbitrary function on each time slice. It's not an arbitrary function of t and theta, as I told you. The dependence on t is fixed. But what does it mean? That on each time slice, I can choose the dependence on theta arbitrarily, and then simply what I know is that the evolution of what I've chosen along time evolution is fixed. Okay, or if you wish, this parameter is satisfying some differential equation in t. But whose initial data on a given Cauchy surface, if you wish, are an arbitrary lambda theta. So I have an arbitrary dependence, which is already something very different with respect to what we have done in order to define Komar mass. In Komar mass, the parameter that entered the mass was the killing vector, and the killing vector satisfies differential equation. There is no arbitrariness in the killing vector. It's a fixed. So the components of the killing vector are, in some cases, very complicated functions, but are fixed functions. So there is no arbitrariness. While here we do have an arbitrariness into the game. What is the factor of this arbitrariness? This arbitrariness is an arbitrary function of theta. What I'm going to do in a while, I expand in Fourier mode this arbitrary function of theta, and this means that I have an infinite number of charges. So that is the first time that we see an infinite dimensional symmetry, in a sense, because I have infinitely many conserved charges, which just correspond, we are going to see it concretely, to the modes of this charge. But before continuing, let me look at what happens if I look at the time dependence of this quantity. So is this charge that I define conserved or not? And well, the answer is almost, in the sense that I can do a small computation here. Okay, that is trivial, but then I can use, say I don't copy everything, but just the term with a trace. And the term with a trace, I can use the equations of motion for this guy. Okay. And why I can do this? Because I settled the problem in such a way that this object is preserving the Lagrange multiplier. So this means that the gauge variation of the Lagrange multiplier is equal to 0, and this means that I can, I mean, it's fixed, and then this means that I can substitute this term. And if I do this, eventually I end up with a term which is just the trace of, so this term here and this term there cancel, and eventually I remain only with this term here. What does it mean? It means that the charge is conserved as far as AT is constant. So that looks something bizarre because we should expect these charges to be conserved. But the fact is that here I had, where it was, the variation of Q is equal to that, and I decided to integrate it in a trivial way. So I decided to integrate to say that Q is equal to the variation of this object here, but of course I can add an arbitrary function that do not depend on the fields. And this ambiguity in the charge, so I can add something else, is something that can cure this problem in the sense that I can define a conserved charge, and the conserved charge that I can introduce is just a sort of Q hat of lambda, which is equal to Q lambda plus K, so 2 pi. Well, I need some space here. Let's do it like this. And I have a right to do this because AT is not a canonical variable. So then the variation that passes there is completely sensitive to what happens to A theta, or if you wish, even the delta of A theta at the boundary is equal to 0 by definition. Into this game. And so this charge here is conserved. So it's true that to all the symmetries that I have in this particular case, I can associate a conserved charge. It's just that maybe the way of getting it is not so direct as soon as I use an arbitrary Lagrange multiplier, an arbitrary boundary value for the Lagrange multiplier. Although in most situations, people consider them to be constant. It's even simpler somehow, but at the boundary, you can also do this. But okay, so that was just a sort of side comment. The thing that interests me more is just that this Q lambda is equal to this object here. Okay, and now yes, because here I have a delta Q is equal to something, okay? And then I decided to say that, well, let's write it. I don't write the integrals, but just let me say something like this, okay? And then I solved it by saying this one, and that's it. Sorry. Because A theta do not depend on the canonical variables. But what is the thing that I used here? I just use the fact that delta lambda is equal to 0. Okay, but this means that, of course, here I can add also whatever function of an object that do not depend on A theta as well. In particular, here what I've done is to add this. Again, is schematical because there are integrals, other stuff, but schematically what I've done has been this one. And here I profit from the fact that at the boundary, delta AT is equal to 0. So this type of term I can always add. So it's just that when you have this kind of equations, you can always add a constant, essentially. Yes, you do define an equivalence class of charges, although that this equivalent class of charges, somehow there is one representative which is nicer with respect to the other, because there is the one that is explicitly conserved in time. In practice, nothing changes, because also this one, you do not have a conservation in time, but the variation do not depend on the arbitrary, on the canonical variables into your system. So this means that this charge is secretly conserved as well, because the time evolution of this charge is just a fixed function of time that you define from outside. Yeah. But it's just because it's a bit bizarre, this kind of manipulation, because you expect them to be conserved, and they are almost conserved, but there is this kind of subtlety in order to fix them. But that is already showing us, again, we learn something that we'll encounter also later, and it is the fact that typically the charges are not defined unambiguously. So you always have some ambiguity in their definition, and sometimes this ambiguity is really crucial because they can change their physical properties even. Okay, so yes, there was a question. Yes.
Would you please repeat where the lambda d theta at came from?
The lambda, this term there. Yeah, so I'm just saying that I want to fix the asymptotic form of a theta. So first of all, the first things here is just enter with a derivative. Now, in this particular case, it's clear what I'm going to do. So I'm just using the equation of motion, and I substituted it with a commutator. In the other case, I'm using the fact that anyway, I want to have the dependence in t of lambda is fixed by the fact that I do not want to change the time evolution. And so here I'm just reconstructing the equations that lambda must satisfy, so which is a delta at is equal to 0, essentially. And this is something that we already encountered because it was the equation that was fixing the t dependence on lambda. Yeah, you can see either algebraically by saying I want the delta at is equal to 0, or you can just look at this stuff and say, well, whatever it is, the t dependence on lambda is fixed, and then I can substitute for it. But okay, that is not the most, no, okay, it's important since I presented, but the things that interest me more now is to understand what I can do with these charges. In the sense that now we go back here. So what's the situation? So we have a gauge symmetry, we impose some gauge fixing condition, we argued that we arrived to have a set of second-class constraint. Now I have this set of second-class constraint. If I have a set of second-class constraint, I can compute the Poisson structure induced on the surface of the constraints. How I do this? I just use Dirac bracket. And how Dirac bracket is defined in this particular way. So I take two phase space functionals, and their Dirac bracket is defined as being so why I'm doing this stuff? Because what I've done, I imposed these conditions, and I obtained some variables, a theta, defined at the boundary. So what I'm finding is a sort of boundary phase space. So I started from a theory which is trivial. I imposed some boundary conditions, and I found some variables that lives at the boundary. And now I want to characterize the phase space of these boundary variables. So this is a purely classical consideration that I'm doing, but well, in the cases of ADS, 3 was considered a sort of precursor of ADS-CFT correspondence, in the sense that all the dynamics of the boundary theory is holographically encoded, in a sense, into boundary variables. In this particular case, is a bit of overshooting, in the sense that there is no dynamic into the bulk. There are no degrees of freedom, but you have solutions like black holes or whatever. So everything is encoded in these variables, small a theta, that are variables that lives at the boundary. And now what I want to do, I want to understand what is the symplectic structures of these variables that lives on the boundary, which once again is an operation that you will see in a bit more complicated way in more complicated situations. And in particular, what I want to do eventually is to understand what is the, as I said, the symplectic structure on the boundary. So I want to be able to compute the Poisson, the Dirac brackets of the residual A theta. But in order to do this, here we are going to pass through a trick. And what I want to do is to first show that these charges here are actually, so the Q's, the generator of the residual symmetries. What I'm trying to say is that you say, well, come on, you already told us, it's that one. But that was before I imposed the constraint. That was the relation that I had, and this relation was that the gauge transformations are somehow generated by a first-class constraint. Now I throw away the first-class constraint, and what I want to show you is that the Q's, so the boundary pieces into the charges, canonically generates the residual symmetry via the Dirac bracket. Okay, so I reduce the phase space. I only have variables that live at the boundary and satisfy the boundary conditions. I still have an object that is defined purely on the boundary, which are these Q small lambda. And this Q small lambda will generate the residual symmetries that I interpret as asymptotic symmetries directly on the boundary. Okay, that looks complicated. It's easier to see why this is so. And the idea is relatively, yes, sorry, and a bit of notation. So here I called all the constraints in this way. This is the set of all second-class constraints, and Cij. Okay, so this parenthesis means that is really a set, sorry, and this is a Poisson bracket, and this is the matrix of the constraints. So these constraints are second class. What does it mean that these constraints are second class? Means that this matrix is invertible. If you have a first-class constraint, simply say that if you take all the constraints inside of your Hamiltonian theory, you compute the Poisson bracket between them, and you have some degenerate direction. So the matrix associated to all the Poisson bracket has a kernel, and this kernel corresponds to the existence of the first-class constraints. Here I argue that there are no first-class constraints anymore, so this matrix is invertible. I can invert it. This matrix here is the inverse of the matrix there, and I can define the Dirac bracket. And okay, so now I define for you what is the Dirac bracket. And then I can do something. So I want to see what happens if I compute the Dirac bracket of the charge with an arbitrary function along phase space. So a priori, computing the Dirac bracket, it may be a huge mess. In this particular case, I will show you that actually this kind of object is easy to compute, essentially. And why it is easy to compute? Because on the constrained surface, these two quantities agrees, because on the constrained surface, essentially, the bulk part of G lambda is equal to 0 on the constraint. And this quantity there is somehow easy to compute because I just apply the definition of the Dirac bracket and it is that one, where now the phi j are essentially the constraint, the first class constraint. And again, this is not a Poisson bracket. I don't know how to denote a set, but this is the set of all the possible constraints that I'm used. So the first constraint was that the first class constraints that f rho theta is equal to 0, that I wrote it, when I use this symbol, is just this Smirig function that is vanishes at the boundary. And the other one, I just wrote a rho because the B does not depend on the canonical variables. Saying that a rho is equal to some function that do not depend on canonical variables is the same as saying that a rho is equal to 0 for the sake of computing the Poisson brackets here. Okay, so this is, I add these two constraints now. And since they are two, they could be a second class constraint. If it is alone, it has no chances to become a second class constraint. Okay, so for the moment, it's just the definition of this stuff. But now, the important thing is that that this quantity is equal to 0 on the constraint surface, which means that eventually, in this particular case, but only in this particular case, if I look at the variation of at the Dirac bracket of the generator of gauge transformation with any functional on the phase space, due to the fact that this object is the generator of the original gauge transformation before I did the gauge fixing, eventually I find that the Dirac bracket of the charges is equal to the Poisson bracket of the G's. And so, again, that's as far as I... So this is one of the simplest way of determining this Dirac bracket on the charges, which is something that with covariant techniques is more complicated to understand from where it's coming from, but here is really transparent. So you really start from the Poisson bracket before you impose the constraints, and after you impose the constraints, you get exactly the same algebra. And this will allow us to compute it. And why this is true, we can go here. So to verify that this is true, we just check it in the two cases that matter. So what we have to compute is this one and see what gives, and this one. But this is just delta lambda a rho, and this is delta lambda f mu nu. Well, we'll have to check just rho theta, because that is only the constraint, but just to let me even be slightly more general. And this is equal to 0 by hypothesis, because I constructed everything in such a way that delta a rho is equal to 0. And so somehow this is my gauge fixing condition that imposes this. And in this particular case, instead, you just find that this is the commutator of f mu nu with lambda. So that is just the transformation of a field strength under infinitesimal gauge transformation. It's the same transformation that you have in Maxwell eventually. But this means that this is equal to 0 on the constrained surface. And since it is equal to 0 on the constrained surface, this means that on the constrained surface, this condition is satisfied. So the conclusion is that eventually, so I found that, sorry? This one? Well, because f rho theta is weakly 0. So it's not true for all of them, but in the case of the constraints, it is 0. So it's again proportional to the constraint. So in this sense, it's weakly 0 by. Okay, so final result is that so this quantity is computed is really the one that I need, is the Poisson structure on the reduced phase space, which is the phase space of my theory. And this is a computation that I can do before imposing any constraint. And so I can easily do without any problem. And maybe just a remark, because it will be important shortly. So here I got that this quantity is weakly equal to 0, but notice that I haven't written here a g, say, gamma, but I wrote f rho theta. Why? Because this is 0 only if I take a generator of a gauge transformation that goes with a generator of a gauge transformation with a smearing function that goes to 0 at the boundary. If instead I allow for a non-trivial boundary value, the result is really radically different. And yeah, do I have a space to do it? Yeah, I can do it above. Because instead, if I allow for an arbitrary smearing function, what I obtain is something very different. Okay, so this is the first piece, and you can say, okay, come on, constraint, give me constraint, it's still okay. But in general, I have a central extension here. That is there provided the gauge parameters are some dependence on theta. So they are not there for constant gauge parameters, but in general, I can have a dependence on theta. So let's first prove this, and then I will comment this one, because this is another thing that you will see everywhere if you want to play with asymptotic symmetries. So let me begin by proving it. And the proof is just by direct computation, so it's nothing deep. But since it's an important result, I'll do it. So in this kind of manipulation, what you do is always this. So you always use the fact that the generator computing the Poisson bracket of a generator with something is the same as taking its gauge variation. And then in practice, you compute the gauge variation, which is easier to handle. And this means that this becomes k over 2 pi integral on a disk d rho d theta of the trace of what? Now I do the variation inside. So I'm taking variation of g gamma. So the term will be gamma times f, the constraints, f rho theta. But I have to look at the variation of f rho theta. And the variation of f rho theta we already discussed takes just this form. Then here we close, minus k over 2 pi integral over S1 at the boundary, because I also have a boundary term, d theta trace of gamma d theta lambda. Okay, very good. But now on the, here I can just use the cyclicity of a trace, and if I use the cyclicity of a trace, I write this term as gamma, as the commutator of gamma with lambda, f rho theta. Well, let me put also the trace just to emphasize that I use the cyclicity of the trace to rewrite it like this. And this is precisely the bulk contribution to this term with the commutator there. But in order to reconstruct this guy, I also have to reconstruct his Q, the right Q that is inside. And this can be done just by rearranging this stuff here, in the sense that in this particular case, I can look at something that, where it is. Sorry. Essentially, this stuff here, I want to rewrite it as being equal to the trace of gamma delta of a theta, so the trace of a theta lambda. And this term here, eventually I can reorganize it as being the trace of gamma lambda a theta, and I can absorb it inside here. So eventually you see that there is a remaining term. No, what the hell did I do? Yeah, and so eventually you see that it remains, no, sorry, I did the contrary. Sorry, that was the delta, sorry, my fault. That was the delta a theta, and the delta a theta is just d theta lambda plus this contribution here that I can reorganize. Okay, and so these two terms here reconstruct G of gamma lambda, but it also remains a term of this form here. Well, sorry, not this one, but I have a leftover term, which is that one. Sorry? I'm not quantizing anything. So this is just the statement is that somehow here you have an algebra of residual gauge transformations, and the statement is that the algebra of charges is a projective representation of the algebra of gauge transformation. So I get a central term without quantizing anything, but it's not a surprise, because the fact of having a central extension, you are used of seeing central extensions that come out from quantization, but central extensions are just a characteristic of projective representations of algebras. So, or if you wish, this is a two-co-cycle of the algebra that I can add. But the correct statement is just algebras gives you, charges give you a representation of the algebra of residual symmetries or asymptotic symmetries, but a very specific one, a projective representation. In general, it's not always true that you have a central extension. For instance, here I need to have a theta dependence. And for instance, another fact that it's always true in general is that if my symmetry, residual symmetry, is an exact symmetry of a background, not just an asymptotic symmetries. In this particular case, an exact symmetry of a background, an exact symmetry in the case of Chern-Simons will be the same as in Yang-Mills. An exact symmetry is something which is a parameter which is constant. no theta dependency, like in Maxwell, no? The one that you have seen the first lecture. In this particular case, no theta dependence, there is no term of this type there. There is no central extension. And this is true also in gravity. If you evaluate the algebra of charges on a Killing vector, no central extension. But if you have other residual symmetries that are not Killing symmetries, then you may have a central extension. So in particular, central extensions are characteristic of infinite dimensional enhancement of asymptotic symmetry algebra. So if your symmetry algebra is just given asymptotically by the same isometry of a vacuum, no central extension. Yes, that's true, but I mean, the fact of getting this central term depends on the specific way you are quantizing. I guess you have in mind the Virasoro symmetry and the fact that it comes out with an anomaly.
This means we have an anomaly in the quantum field, right?
This is a counterexample, if you wish. So in this particular case, if I remember correctly, but I cannot point to a very precise reference. The fact is that if you quantize, you renormalize the central charge. So the central charge could receive quantum correction even if it is already there, in a sense. But the statement is just this one. So it's a very precise, if you wish, even mathematical statement. It has something, well, let me first write this statement. And the statement is that the algebra that you see here is exactly the same also for these other charges here. And so the statement applies to this one, to the second line. So the first line of this box is just a tool that I use to derive the second one. And the second one is that these are really the charges. And what are the ingredients inside this statement? The first ingredient is that I'm able to compute a Poisson bracket on the reduced phase space, or if you wish, on the asymptotic space, this Dirac bracket here. Second statement is that the charges are generates the residual symmetries, which is something that is written here. And since these charges generated the asymptotic symmetries via the Dirac bracket, I can compute the Dirac bracket of the charges. So I can compute the canonical structure of the charges and the algebra of the charges, because this is the algebra of the charges. This is the precise definition. So the Dirac bracket on the reduced phase space of this object. The algebra of the charges gives you not a representation of the asymptotic symmetry algebra. In this case, it would be somehow the asymptotic symmetry algebra just given by this commutator, but it gives you a projective representation of the asymptotic symmetry algebra. And that is always true. And with additional thing that is rare if you don't go to asymptotically flat spacetime, it's rare to see this, because the additional statement is that the central extension is trivial if you are considering exact symmetries of the background. This is why in more standard setup you don't see, but as soon as you have an infinite dimensional enhancement, is always there, this kind of central extension. Okay, so with these two statements, somehow we have seen all the structure that emerge in all possible, most complicated applications of the study of asymptotic symmetries that you can encounter. So what is your goal is that you have to define, to set up boundary conditions, look at residual symmetries, find a way to compute surface charges associated to these residual symmetries, check that each residual symmetry is associated to a non-trivial charge, which means that it is generated on the reduced phase space, is canonically generated by a surface charge, and then you can compute the algebra of surface charges, and the algebra of surface charges typically is a projective representation of the algebra of residual symmetries. That's it. That you will find everywhere. That is the context in which I was able to prove in a finite amount of time all the steps that arrive to that leads to the final result. So now this concludes all the machinery in this particular case. But now, since we arrive up to the end, well, let's try to look at this reduced phase space, how it looks like in this particular example that we have seen. Okay, that is the general framework, general machinery. Well, not completely general in the sense that I took the liberty of imposing some specific boundary conditions that are here, but the final result is pretty general. So, yeah, I haven't done it in full generality, but the conclusion that I reached apply to more general context. And now let's look at what is really the form of a Poisson bracket on the reduced phase space. And in this particular setup, which once again is just a sort of working example in which things are the simplest possible ones. Yeah, to see at the end, all my liberty is encoded into these functions here. And where the t-dependence somehow something that is not interesting because I'm interested to look at what happens on a given time slice. So in order to do this, I just expand this object in Fourier modes in theta. And these are the generators of the algebra. Okay, so I have this arbitrary A theta. I expand it in Fourier modes. And now I use a small trick. And the small trick is that if I look at a specific mode, Pt, this object I can also re-express thanks to the, say, manipulations that we have given above. I can also express in this particular form. Okay, how can I check? I just you take this expression here. This is a very specific gauge parameter, if you wish, because it's a Lie algebra valued object with a functional dependence which is fixed, where P now there is no sum here, it's a very specific P. So I'm just projecting on a particular P. I take this particular gauge parameter, I throw it inside the expression for Q, which is, of course, GAN, but say, well, this guy here without the delta, and I obtain this thing. How can I obtain this thing? It's because, well, I get a delta function because I have this I'm integrating over theta with E ala EI pi theta. So you can do the small exercise of checking that indeed this is correct. And then, since I know the algebra of charges, this means that thanks to this identification, I can compute the algebra of the modes here. And the algebra of the modes is just the following. So in the specific case, of the three-dimensional gravity, with this boundary condition that I've imposed, the result that I got is an SL2 affine algebra. So this is a Kac-Moody algebra. So with a central extension. So this looks maybe very disappointing if you already knew something about 3D gravity, because here you expect to see the conformal symmetry, but I have cut smoothie, not conformal. So what's going on? The point is that the boundary conditions that I used have been chosen for pedagogical purposes, but are not boundary conditions which are really appropriate to describe three-dimensional gravity. So the boundary condition of three-dimensional gravity have been discussed early 80s by Brown and Renault, and are, if when translated into the Chern-Simons formulation, are not the one that I used just because they are the simplest one to get the result. So now we are gonna see the effect of boundary condition. Here I set up some boundary conditions that are perfectly fine, give me charges which are finite. I can have all the solutions that I like inside the space of solution, and give me some asymptotic symmetries, but the asymptotic symmetry is not the one originally found by Brown and Renault. Here you see that if I change the boundary condition, I can change the asymptotic symmetries, which means that I can change the boundary phase space. So in a sense, I'm changing the theory. In a sense. No, well, I'm changing the theory without in a sense. And yes, so now the last step, and then we will move in the next lecture to the four-dimensional case, or for two more general cases. But before closing this example of 3D, I wish to get to explain you how to get the conformal algebra and how to recover, well, or at least to quickly explain how to recover the result of Brown and Renault.
So in which sense these boundary conditions are less appropriate for 3D gravity?
That is again is a matter of so now they have been rediscovered say 30 years later, and now they are called the most general boundary conditions for IDS3 gravity. So it's a matter of choice. The boundary theory is different in a sense.
So you don't have the black hole.
No, you do have a black hole inside. So in a sense, they are perfectly fine. As I told you, so now I still like to see them as a kind of pedagogical introduction to go to the other ones, but I think that the correct statement is that they are not the Brown and Renault boundary conditions. That is the point. Now, if the Brown and Renault boundary conditions are the correct boundary conditions to discuss gravity in 3D, it's maybe unclear. So, in a sense, one possible thing could be that maybe the boundary conditions that are good are the ones that allow you to quantize the theory or to do some other stuff. From the viewpoint of the basic requirement asked by Brown and Renault back then, these boundary conditions are as good as the one of Brown and Renault. What is the difference? Why Brown and Renault didn't start from this? Because in the 80s they didn't know the Chern-Simons formulation, and they started from the metric formulation. And the metric formulation with boundary conditions looks crazy. So they are very unnatural there. While they are the most stupid things that you can do in Chern-Simons, they are a bit convoluted if you want to express them in the metric formulation.
There is an explicit expression.
Yeah, there is an explicit expression. So there is a paper by Grumiller and Riegler, which is called the most general boundary condition in IDS3 gravity, but it's just this. Essentially that well, okay, I don't want to diminish the paper, but just so somehow these boundary conditions with some subtleties, because they, what they did, it was to handle correctly the Lagrange multiplier into these things. So, but say with being a bit cavalier about how to handle the Lagrange multiplier, they were already around since the early papers on the Chern-Simons formulation of gravity. But you had to be a cavalier about this part. But one nice thing is that in this paper by Grumiller and Riegler, they translated the metric formulation. You see how horrible they are in the metric formulation, in a sense, which is may explain. Yeah, somehow Brown and Renault computed asymptotic symmetries before knowing the existence of a BTZ black hole and before knowing the existence of a Chern-Simons formulation. So in this sense, they were way ahead. And the paper is maybe not the most, say, easiest thing. They do a lot of crazy ad hoc stuff, but they got the right result before going there. Okay, so what I can, well, maybe this I keep. Well, the other one I can erase. Okay, so now so in my notes, I called this section asymptotic ADS3 boundary condition, but in view of the discussion, let me change it in Brown and O boundary conditions. So that is what historically were supposed to be the boundary conditions for asymptotically ADS3 gravity. And we can discuss it, but there are a different set of boundary conditions. This is a fact with respect to the one that I have imposed. So now, although again, I could just give you the result of the Chern-Simons formulation, let me try to motivate why they take a different form just by going back for a while to the metric formulation. This is just a motivation. So I have a right to choose the boundary condition that I like, provided it gives sensitive results. But now let me try to motivate why in the early 80s people looked at these boundary conditions. And the starting point is that I want to have something which is asymptotically ADS. So it looks wise to start from looking at how ADS looks in 3 dimensions. And for that, I can use a global parametrization of ADS. And if you remember the discussion that we had at the very beginning of the discussion about three-dimensional gravity, the fact that this is a global parameterization is pretty important because locally everything looks like ADS. But now I want to be sure that what I'm dealing with is really ADS, not just something that locally looks like ADS. And that is a global parameterization of ADS. So the coordinates rho, t, and theta cover the full ADS3 surface. How can I get it? For instance, I can start from the parameterization of ADS as the surface such that you have something, you go to a sort of ambient space. You impose this condition here. So ADS3 is a sort of Lorentzian hyperboloid embedded where I have an eta AB, which is equal to minus plus minus, embedded into a flat space-time with this signature. And you can check that you can introduce coordinates rho, t, and d theta such that this metric ds square is just eta ab dxa dxb on the constrained surface where x square is equal to minus L square. And you can parameterize it, and you really see that these coordinates cover the full ADS. Or you go to Hawking-Ellis, where they discuss several parameterization of ADS, and you check that this one is the 3D version of the global parameterization of ADS, as you wish. The two are equivalent because we are talking about a constant curvature space-time. And now, one thing that you can do is that these coordinates are not the one I'm going to use. I just do a stupid change of coordinates, and I'm just sending rho in rho plus the logarithm of 2. You said, why are you doing something so crazy? It's just to match this parameterization, which is the one that is probably familiar to, at least to some of you, to the one that is typically used in this three-dimensional context. And if I do this redefinition, I end up with a delta S square, which is equal to L square d rho square plus E2 rho plus 1/16 E L minus 2 rho minus dt square plus L square d theta square Okay, and now, so I have written everything in terms of t and theta because are the variables that I used in the Chern-Simons formulation, but clearly this stuff here, you can just write it as being, so how it is, this is dx plus, so you can write everything in terms of, say, x plus minus, which is equal to minus dt square, dt square plus or minus d theta square, dt divided by L. So this is something that you can find often in the literature, but for what I want to do, it's more interesting for me to leave it like this. And now I can go here. Now, what I want to do now is just to translate this global parameterization of ADS into the Chern-Simons formulation. And if I go into the Chern-Simons formulation, the global parameterization of ADS in these particular coordinates just becomes something pretty simple. And here I put a plus or minus as I anticipated. This is just because I want to deal directly with the two copies at the same time. So A plus is A of the previous lecture, and A minus is A twiddle of the previous lecture. And then you have this plus or minus D rho plus or minus E rho L plus or minus 1 plus 1/4 e to the minus rho L minus plus 1 dt. So L plus or minus d theta. Okay, it is what it is. How I got this one? I have a metric. If I have a metric, I can compute the Filbine and the spin connection. Once I have a Filbine and a spin connection, I take the combination of the two. So these A plus or minus ADS are nothing but omega ADS, say A, plus or minus 1 over L E ADS A. Okay, and I recall you that essentially the things that I have to get this one is this. And while the spin connection is fixed by this relation here. Okay, so a priori, this means that for any given metric, I can find an equivalent class of Filbines. Why an equivalent class of Filbines? Because I can always act with a Lorentz transformation and change them. So this identification between the two is not one-to-one. There is an equivalence class here because these objects transform under local Lorentz transformations. I can clearly do a local Lorentz transformation and I get something equivalent. And once I fixed the form of my Filbine, then the spin connection is fixed by this algebraic equation here. That is the way these things have been obtained. Clearly, if you know the result, you can just do the opposite. So if I know A plus or minus, I can compute omega and A by inverting this relation. I can plug it inside this relation here, and I can verify that these guys give precisely for me the desired form of the metric. Okay. But it's a good exercise if I write this quickly or quickly erase. If you can rederive it, is a useful exercise, I would say. And just to set completely the notation, so that was the definition of this object. But another information that is missing, you see this L0, L plus or minus 1, L minus or plus 1. What are these guys? These are just the generators of SL2 R that now I write in a slightly different basis. I just changed basis, and this is SL2R. Nothing more, nothing less. Okay, so this is just a parameterization of anti-de Sitter space. But now the advantage of this parameterization of anti-de Sitter space is that I can look at it, and again I do a small algebraic manipulation, and you can realize that this stuff can be written in the following form. Okay, why is this the case? Because when I have this b minus 1 L b rho, so I can commute this guy with this guy here in order to eat this one and having some certain dependence on rho that is coming out. But the commutator that I take to do to take the two is bringing some powers of rho around. So essentially, once again, just a small computation. You can just have to have b passing through. Yes, but with this information. Okay, this is just a rewriting of the ADS metric in terms of the Chern-Simons variables. And now, if I compare this form of the Chern-Simons metric with the boundary conditions that we have used of the Chern-Simons variables, well, if I compare this form of anti-de Sitter space rewritten in Chern-Simons variables with the boundary conditions that we have used before, you see that there is something, well, we can see, sorry, actually here, that is something a bit weird going on, in the sense that that is the form of anti-de Sitter. If I allow for a completely arbitrary a theta, for instance, this means that I may allow for something that close to the boundary grows or explodes with respect to the ADS metric, because the ADS metric has a very specific dependence on rho. If here I allow for an arbitrary dependence on rho, on other stuff, I may find solutions that are completely that are completely out of, I mean, that they do not approach anti-de Sitter at the boundary. And in this language, the Brown and no boundary condition are just the following, are just stating that A plus or minus theta minus A plus or minus theta of ADS, well, or let's do it like this. So when rho goes to infinity, I want to asymptotically approach ADS3. And in this sense, these are reasonable asymptotically ADS3 boundary conditions. So now I know with the, say, with the proviso that, yeah, let me see, with the additional conditions that I want that this factorization of the radial dependence also continue to hold. So essentially, I'm keeping the same radial dependence as in the ADS3 case, and I'm imposing the additional condition, this additional condition here. And the result is that if I do this, well, and of course the same is true also for this one. So the setup is identical to what we have seen before, but on top of this, we are adding this one. And since the radial dependence is encoded in this function b rho, you can just compute what is the effect of this extra condition that we impose. And this extra condition that we impose is just telling us that on each time slice, The dependence so the A theta is not arbitrary, but asymptotically must take this particular form. And I'm working here, I stress on each time slice. Why I'm stressing the fact that I'm working on each time slice, because I can also take into account the arbitrarity dependence, but this depends on how I fix the Lagrange multiplier, essentially. So it depends on an additional external choice. So one convenient choice is AT equal to minus A theta. So I can fix the Lagrange multiplier to satisfy this particular choice. This choice is consistent with everything, but then if I have this choice, which just means that, yeah, I think it's like this. So if I impose this extra, for instance, then the result is that this condition is equal to 0, and if you have this condition is equal to 0, then you discover that you have a relation of the type and these functions become just chiral functions. But that is not necessary what you see here in this box. It's just an additional condition that I can add. It is very convenient in most cases, but in some cases, it doesn't work. So in gravity, I can do it. If I do it, for instance, in these Eiger spin gauge theories, if I impose this condition, I killing all the black hole solutions. They do not belong to the space of solutions. So I have to be careful. So for this reason, I just ignoring this subtlety and just focusing on what is going to happen on a fixed time slice. But the important thing is that you see that, imposing this condition, which is a very reasonable one, puts some constraints on A theta. And constraints on A theta means that I have to modify the setup that I've seen before. And just to conclude, at the level of the metric, what is this imposing? Well, I can introduce the radial coordinates of this type. So where this is just ADS radius, and I take the exponential of rho, and then the metric which is associated to the connections that satisfy this condition there just takes this form. And that's is what is called the Pfefferman-Gram form for the metric. So I'm in the so-called Pfefferman-Gram gauge. You see that here there are no mixed terms. So I and j are just boundary coordinates in 3D. R is a radial coordinate. So I don't have any term of the form GRE. So I fixed this. And GRR is completely fixed. So this means that I fixed a total of 3 conditions which correspond to the 3 independent diffeomorphisms that I can act on the metric. So it's a fully fixed gauge. And this is showing you that essentially the counterpart of my residual gauge fixing here is the Pfefferman-Gram gauge fixing in the metric formulation. So they are completely equivalent, the two. And then the additional condition that I imposed in the Pfefferman-Gram metric means that the boundary metric is flat in the Brown and no boundary conditions. And of course, this is something that you can modify, and there are a lot of works that try to modify this setup. But this is the basic one. So demanding this corresponds to the fact of demanding that the metric in Pfefferman-Gram gauge is flat. There is a one-to-one correspondence with this, then you can like or not to like, but this is what are the Brown and no boundary conditions. And okay, so now we are almost there. Eventually, it has been a long detour, but can go here. Voila. So now we are, yes? Yes. To because you wish that I mean, if I fix the gauge transformation like this, then say naively you can plug this one inside the equations of motion, and if you plug this one inside the equations of motion, is give well, okay. So this one to this one is just a change of coordinates. Okay, no, because it's just that AT with A theta is just a change of coordinates. And then how you arrive to this one, that's just a matter of imposing the equations of motion. And in particular, the equations of motion comprises also Ft theta, say, equal to 0, because this is just the evolution equation for AT. So when I fix remember that from a Hamiltonian, so the simplest answer is just you impose all the Chern-Simons equation of motion, and non-shell this is true. From an Hamiltonian viewpoint, what I'm doing is that I'm fixing this arbitrariness that I have here, and since time evolution is a gauge transformation generated by a gauge parameter, which is just the Lagrange multiplier, say the Lagrange multiplier is a gauge parameter per unit time under time evolution, then you get the equations of motion give you this condition on L. And now we can arrive up to the end. Now I have two options. I'm following the option which is maybe less common, just because, well, the other one, I leave it to you as an exercise. Now I have an additional boundary condition. So I have two options. Option number one, I restart the machinery from scratch. So what does it mean? I have the radial gauge fixing doesn't change, but now I do have a boundary condition. So I have to compute also delta A theta. I compute delta A theta, and I look for the residual gauge transformations that preserve this additional condition here. And the result is that I will have some residual gauge transformation with a gauge parameter that do depend on time, on the field variables this time. And so this means that not everything is guaranteed, but if I go back to the formula that, of course, I just erased, so the variation of a charge. The formula for variation of a charge is always the same. Now I have a gauge parameter that depends on the fields and a specific delta A theta that I found after that. I throw both of them inside the variation of a charge, and in this particular case, by magic, all the terms that are depend on the field, I mean, all the terms that are non-integrable cancel, and eventually the result becomes something that is linear in the fields, and so I can integrate. So that is the standard way of computing it. Let's say I leave to you as an exercise. In case you have problems, we can discuss it, or we can have a look at it during the discussion session. So here I take just a slight different perspective, and the slightly different perspective is that I can also think of the fact that I impose additional constraints on top of a phase space that I defined for you before, the Katz-Moody phase space that I defined for you before. And now let's see what these additional constraints do. And I go back to the phase space that I found before. So I've chosen this way of doing it for two reasons. One reason is that the other one, you take any random review about 3D gravity, you will find this computation, but really random. So don't think too much about how to take it. While this one maybe is less common, and because it also allows me to stress some additional facts about this kind of process that we are encountering. So that is just, I'm writing in the particular case of SL2 R affine algebra, the generic algebra of modes that we have computed before. And now what I have done is that I added an additional constraint on top of it. And the additional constraints well, now maybe just to fix the notation, these L are what before I called A. So I'm just expanding okay, it's just precisely the modes that I had before. And the additional constraints that I'm putting on top is the following one. And the first means that L1 P minus K delta P 0 is equal to 0 for the modes. And this one, I can also write it, see it as a constraint for the modes. So that's for theta, and this is the same as saying that L0 P is equal to 0. Okay, so that's are the constraints that follows from the fact that here, say I took just the plus copy. For the plus copy, I just have this fixed. And here I have the only variable that I have, the only mode that remains, the one associated to L minus 1. So this means that the L1 function, well, has been set to 1 because there is this term here. And the L0 has been set to 0. That's it. And now I have these additional constraints, and I have a Poisson structure that was the one that I computed for you before. And now we see these constraints that I added are first or second class. The answer is here. I just look at what are the metrics of the constraints. And the metrics of the constraints, what do I have to do? So I have to look at L1 with L0. L1 with L minus 1, I don't care because it's not inside the constraints. And I have to look at L0 with L0. And then I can look, I can compute the metrics of the constraints. Oops. And let me introduce a little bit of notation. So Phi1P is equal to L1P minus K delta P 0, and Phi2P is equal to L0P. And the matrix of the constraints, it's something that I can write as in this form. And on the constraint surface, it is equal to 2K delta P plus Q 0, 0, 1, minus 1, minus IP. So why this is the case? Because essentially the first L1, L0 that I have written here, where it is, yes, this one L1, L0 on the constraint surface is equal to just 2K delta P plus Q 0. But this means that in both cases I have a delta here. So this means that there is really a second class constraint. So there is something that does not vanish on the surface constraint, on the surface of the constraint. So you just see that these metrics can be inverted, and then I can compute the Dirac bracket. So these are second class constraints, and I can compute the Dirac bracket. So I compute the Dirac bracket, and then I introduce just for simplicity or to complain with the standard notation. So the only variable that remains is LP. I introduce this kind of notation, and if I compute the Dirac bracket of these modes, what I found is the following. And the Dirac bracket is just the one that I have defined before. And we are almost there to arrive to the result that you maybe realize. The last step is to do this definition. And with this redefinition, I have an algebra which is just LP LQ, which is equal to, well, let's put an I here, P minus Q, L at P plus Q, plus C divided by 12, where C is equal to 6K, which is equal to 3L divided by 2G. And this is the famous Brown and O result that says that the algebra of asymptotic symmetries of three-dimensional gravity with their specific boundary conditions is the Virasoro algebra with a central charge C, which is related to the ADS radius by this particular formula. And essentially, that's it, and you can recover directly this formula just by redoing the computation that you have done before, but working with charges that are associated to a residual gauge symmetry that is field dependent. But like this is a very direct way, yes? No, is what we discussed before is precisely the same answer to the previous question. So this is a purely classical computation, and that's it. It's just that these charges satisfy a projective representation of a De Witt algebra. So you can also just look, if you look at the residual gauge transformation, you can look at the commutator of residual gauge transformation. It's just the usual commutator of gauge transformations that you can compute, and then you will find the De Witt algebra. But then if you look at the commutator of charges, instead of a De Witt algebra, you find the Virasoro one with a C that pops up, but this is a completely classical computation. Looks surprising, I agree, the first time one sees, but that is just a characteristic of the computation of asymptotic symmetries. Algebra of charges is a projective representation, and that's it. And then as matter of interpretation, of course, people, well, you can say, that's a school, I have this stuff there. What can I do? I quantize this, I just work with Virasoro algebra, and I declare that this is the algebra of my boundary theory. And then it's the CFT. And then you can get some results that, what do you do here? So you're agnostic about what is the boundary CFT. You just assume that a CFT arises, and then you try to use universal properties of CFT. For instance, you use Cardy formula, and you derive or you predict the correct entropy for the BTZ black hole. But, well, that is not really a quantization, so just assuming that the boundary theory satisfies this algebra. Yes?
Instead of doing all these steps, we just do a pseudo-random construction, and then we would arrive at the same quantity or a shifted one. Or
I think is a shifted one. That's, to be honest, I should do the computation, but in the case of Sugawara construction, you just make a manifest that there is a conformal symmetries around, or that you can build an energy momentum tensor somehow, but here it's different because it's just a different kind of construction. So if you wish, what is really what I did, and this construction make it manifest, is the construction which is called as Drinfeld circle of reduction, in the sense that you start from an affine algebra, you put some constraints on it, and you get another type of algebra, which is just, in this case, the Virasoro algebra. And that is a construction which is well known in math. Mathematicians worked on it, with a lot of generalizations and nice things. For instance, again, this is just words, but if you play with SLN theories, then you have something that described by Eiger spin theories, and then the Riefel-Sokolov construction and affine SLN gives you what are called W algebras, which are nice algebras because they are nonlinear. And what this algebra tells you, so here what I got is a Lie algebra. So it's already perturbing because there is a central extension, but it's still a Lie algebra. But this is not guaranteed to be the case. So if you look at the algebra of charges of asymptotic symmetries, in general, you don't even get Lie algebras. And that is the case of this Eiger spin construction in 3D, but you don't even have to go to Eiger spins. So you are learning in the SUSY class how to couple fermions to this business. If you work with extended supergravity, I think starting from n equal 4, then you have a nonlinear algebra. Why you need an extended supergravity? Because the nonlinearity are brought by the generators of R symmetry. So I don't know if you're familiar. So somehow, if you want to build a supergravity multiplet, once you put more gravitini, you also need to put some additional stuff, in particular some U1 charges, and these U1 charges give you some nonlinear terms that pops up here. So it's not guaranteed at all that the result is a Lie algebra. But in this particular case it is, and it is always a Lie algebra up to possible central extension. Not all Lie algebra admit them, but that's it. So that is really, it's called sometimes Drinfeld-Sokolov reduction, sometimes it's called Hamiltonian reduction, and it's just you start from Kac-Moody and you kind of curve it, and you get a different type of algebra. So it's a different construction with respect to Gavara, but it's a good question. Simply, I don't know. So it could be that you for sure find an energy momentum tensor, most probably with a central extension, but I should check. So I guess, yeah, perfectly on time, so it worked well.